Let P be a point of a flat surface S and assume that P is not an umbilic point. Then there is a surface patch of S containing P, that is a ruled surface. Okay. So we are given with a flat surface S. What is a flat surface? It is a surface at which the Gaussian curvature K is equal to 0 at every point. Okay, at every point belonging to S. And P is a point on that, and it is not an umbilic point. So P is not an umbilic point means K1 is not equal to K2. The principal curvatures are distinct at the point P. Okay, then we need to show that there is a surface patch of S containing the point P, that is a ruled surface. That is the union of the straight lines. Okay. So we are given with the point P which is not an umbilic point on the surface S. So I will make use of the previous result where we have proved that if P is a point of a surface S and P is not an umbilic point, then there is a surface patch sigma of S containing P whose first fundamental form is U du square plus G dV square and second fundamental form is L du square plus N dV square for E.g. Ln smooth functions here. Okay. So according to this result, we have the surface patch sigma, okay, for S3 that is containing the point P such that its first fundamental form is E du square plus G dV square and second fundamental form is L du square plus N dV square by the previous result. Okay. Now then, what is the Gaussian curvature? We have derived an expression for the Gaussian curvature in terms of the first fundamental form coefficients and second fundamental form coefficients. What is that? Ln minus m square divided by Eg minus f square. Okay. You can see here in the first and second fundamental forms, m and f and m terms are 0 here. So we are left with Ln divided by Eg. But the surface is a flat surface, so at every point of the surface the Gaussian curvature is 0, so this is equal to 0. So once this is equal to 0, either L is equal to 0 or N is equal to 0. Now the fact is that both cannot be equal to 0. Why? If both are equal to 0, then K is equal to 0 of course, then K1 will be equal to K2. If both are equal to 0, then K1 will be equal to K2. That will be a contradiction because P is not an umbilic point. So one of them is equal to 0, the other is not equal to 0 in this case. Let us assume that L is not equal to 0 at the point U0, V0. So let us suppose that L of U0, V0 is not equal to 0. Okay. L is a continuous function, so it is not equal to 0 at U0, V0, then it will not be equal to 0 at in some open subset of U containing the point U0, V0. Okay. So if possible, if necessary, we can shrink the set U, open set U if necessary, and we will assume that this L is not equal to 0 everywhere at the point of U, at every point of the set U here. So L is not equal to 0 at every point of U, then N must be equal to 0 at every point of U. Okay. So once L is not equal to 0 at all points of U, N is equal to 0 at all points of U, then what is the second fundamental form? Second fundamental form of sigma will be equal to just L du square here. Okay. Now we will consider the parameter curves. U is equal to constant and we will prove that these are straight lines. Then the surface patch sigma containing this point P will be a ruled surface here. Okay. So our claim now is to prove that the parameters curves U is equal to constant are straight lines here. Okay. So we can consider its parameterization V sigma of U0 V. Okay, U is constant, so U0 is the constant value of this U, V is a variable here. Okay, so let us consider the tangent, unit tangent vector for this curve. So unit tangent vector of this curve, let me take it as T, and what it is given by sigma V divided by square root of G. Why I am dividing by square root of G? Because we know that G is norm of sigma V square. So I am dividing sigma V by its norm so that I get the unit tangent vector here. Okay. So now I want to show that these are the straight lines. To show that these are the straight lines, the tangent vector must be constant, then they will be straight lines. Okay, so if the tangent vector of a parameterized curve is constant, then the image of the curve is straight line. That is what we know by a earlier proposition. So to show that this is constant, I will prove that its derivative is equal to 0. Okay, with respect to v, it is equal to 0. Now to show that Tv is equal to 0, let us consider the standard unit normal of sigma. Consider n, the standard unit normal of sigma. Then we have proved in the earlier class that its derivative with respect to u, it will be given by a sigma u plus b sigma v, and with respect to v, it will be given by c sigma u plus d sigma v, where these a, b, c, d, they are given by the matrix minus f1 inverse f2, where this f1 inverse f2, this is denoted by w, and this matrix is called as Weingarten matrix here. Okay, so the derivatives of the unit normal. Now for what we have here for this matrix a, c, b, d, okay, it's minus f1 inverse f2, right? And in the fundamental forms, what we have, first fundamental form is e du square g dv square. So here f is 0, and for the second fundamental form, what we have, L du square. So m and n both are equal to 0 here. So all these three terms will be equal to 0. Only a part will be left out. And what is that a? It is f1 inverse f2. So it will be minus e inverse L. Okay. So this matrix is minus e inverse L 0 0 0. Okay. So considering these values for a, b, c, d in this expression here, so what I have for nu is equal to minus e inverse L sigma u, okay, and nv is equal to c is 0, d is also 0, so this is equal to 0. Let us call this as the statement 1 here. Okay, now consider the first expression here, that nu is equal to minus e inverse L sigma u. So I can write it for sigma u, okay, from this. So sigma u is equal to minus e L inverse nu, right? So consider the dot product of sigma u with Tv. So consider Tv dot sigma u, right? So Tv dot sigma u is equal to minus E L inverse Tv dot nu. Okay, so let me call this as the second statement. Now consider T dot nu. Okay, so T dot nu. What is T? It is sigma v divided by square root of g, right? Dot product with nu. What is nu? It is minus E inverse L sigma u. Okay, so we have minus E inverse L divided by square root of g sigma u dot sigma v, or sigma v dot sigma u. Anyway, dot product is commutative. So what is sigma u dot sigma v? F part in the first fundamental, f in the first fundamental form of sigma is 0. So this is 0. So this is equal to 0. So what we have here, T dot nu is equal to 0. And also considering the second statement here, what we have, nv is equal to 0. So if I consider its derivative with respect to u, then this is also equal to 0, because it itself is 0. So this is equal to 0 here. Fine. Now let us consider the dot product. This dot product. Okay. So T dot nu is equal to 0. Consider this expression here. Now differentiate with respect to v. So differentiate with respect to v. So what we get, Tv dot nu plus T dot nuv, that is equal to 0. So from this I can write Tv dot nu, that is equal to minus T dot nuv, and we have proved that minus T dot nu, here we have proved that T dot nu is equal to 0. So this will be equal to 0 here. Okay, so minus T dot nuv is equal to 0, Of course, nuv is equal to 0. I can use this. Nuv is equal to 0. So this will be equal to 0. So from this, what I have that tv dot nu is equal to 0. So if I consider the statement tv dot nu, I have it in the second expression here, right? So this is equal to 0. So tv dot nu is equal to 0 from this statement, and by this second statement this is equal to 0 means this part is equal to 0. So what I have, tv dot sigma u is equal to 0. This I want. Okay, so tv dot sigma u is equal to 0. Now t is a unit vector. We have considered t as the unit tangent vector, so it is a unit vector. So if you consider tv, it is perpendicular to t, so the dot product of tv and t is equal to 0 here. So once the dot product of tv and t is equal to 0, what is tv here? So tv is t here. T is sigma v divided by square root of g, right? So tv dot sigma v divided by square root of g is equal to 0. So what does it imply? It implies that tv dot sigma v is equal to 0. So I want this expression also. So here I got tv dot sigma u is equal to 0. Here I got tv dot sigma v is also equal to 0. Now finally we will consider that t, the unit tangent vector, standard unit normal, they are perpendicular to each other, so the dot product is equal to 0. So let us consider this expression. Again we will differentiate this with respect to v. Okay, so what do we get? tv dot n plus t dot nv is equal to 0. So tv dot n, okay, is equal to minus t dot nv. And what is this nv? Nv is equal to 0 by the statement 1 here, right? So nv is equal to 0, so this part is equal to 0. So what I have, tv dot n is equal to 0. Okay, so what I have, tv dot sigma u is equal to 0, tv dot sigma v is equal to 0, tv dot n is equal to 0. These two are the tangent vectors which are mutually perpendicular to each other, and n is a standard unit normal. So sigma u, sigma v and n, they form the basis for R3, and all these dot products are 0 with the tv here. So tv must be constant. So these three implies that tv is constant. So one tv is constant, this tangent vector t is equal to tv is 0, the tangent vector t is equal to constant here. Okay, so we are getting the ruled surface, okay, because the parameter curves u is equal to constant are straight lines, so the whatever surface we are going to get is the ruled surface.